everyone. Thank you for joining the webinar today. I know a couple more people will be joining. Just to say that this webinar will be recorded and on our website afterwards. And if you have any questions as we go, please use the Q&A function at the bottom, and we'll have a question and answer session at the end. And I will pass you over to Rob, who will be chairing today's session.
Thanks, Orla. Yes, good morning, everyone. Thank you for joining us today. So my name is Rob Millett from Intralerships Management, and I'll be hosting today. I think Orla's done all the housekeeping for us, but a couple of us will be talking throughout the webinar. And if there are any questions, then I believe we can put those in the chat function, and we'll come to the questions at the end. So next slide, please. Sorry about this. Hopefully, a couple of issues with the technology, as always.
It's showing the second slide, no?
Yes, I can see the second slide now. Thank you. Yeah, so today's webinar is Green Retrofits, proving the case for zero emissions coasters. So what I'm going to talk about today is I'm going to start off with a brief introduction of what's happening. Then I'm going to talk about the challenges that we're trying to address in this webinar. I'm going to tell you about the HEROZEC project and how that fits in with the webinar. And then we're going to hear from both the other speakers, Eugene and Ahmet. And then I'll give a summary at the end, and we'll have some time for questions at the end of that. So a brief introduction. So the HEROZEC project, which we'll be talking about, is there to address a few challenges. And this is a project that was conducted under CMDC4 as part of the UK government's UK Shore programme. So the project was funded about a year ago by the UK government in order to try and address the challenges, which I'm going to talk about in the next couple of slides. And the project is run as a consortium between ourselves, which is Intralerships Management, EcoMar Propulsion, the University of Strathclyde, and MarRI-UK. So the challenges we're trying to address here is the main one is the moving regulatory environment. So in the European Short Sea, which is where this is targeted, it's a particular domain of shipping, which is actually one of the underappreciated parts of the global commercial shipping fleet. So the European Short Sea and the Short Sea in general represents around 10,000 vessels. So you can see it's a hugely populous part of the market, albeit one that seems to be at the lower end in terms of where technology appears, and certainly where the general public appreciation of the marketplace is. So for context, the total commercial international fleet is around 100,000 vessels, about 106,000 vessels. And so you can see that 10,000 vessels represent something like 10% of the entire commercial fleet. And yes, it always seems to be one of the last places for technology to appear because of the scale of it, the nature of the trade, the fact that the trade is not on specific routes. The vessels are tramping, the vessel routes, the vessel duration, voyage durations is quite variable, and so it's a challenge that certainly needs to be solved. And at the moment, the people that are in that marketplace feel like the technology is a trickle-down effect. So the technology will come from other sectors. So someone will have, let's say, a battery-powered ferry, then we'll look at where that technology can be transplanted into these vessels. I'll give you a little spec of the vessels in the next couple of slides. But these general cargo vessels always seem to be takers, and people don't develop technology around them. And given the population of these, there seems to be a huge commercial market as well as a huge demand for technology coming. And where that technology is trickled down, the owners in this area don't really have anything that they can immediately rely on. So if you were an owner in this sector and you're looking to see a demonstration of a vessel that was doing what we're trying to achieve, then there is no one to look to. People will see things in the deep sea. They'll see much larger vessels that have known trade routes, vessels that are anything but the short sea. And so there is no direct solution to these problems at the moment. So there seems to be a fast-moving regulatory environment, a fast-moving bar of what needs to be achieved, and yet there is no obvious go-to solution or even anything that's currently possible. So if an owner in this sector, who typically may only own a couple of vessels of relatively low financial value, decided to back a technology, there's a massive risk to that owner. They'll be looking at a technology as something that it has to function correctly. And I mean function in the sense that if they are to invest money in it, they need to know that investment will be a good one. There is no alternative funding. There's no significant company. The fleets are generally between 1 and 5 vessels, apart from a few significant owners. The fleet sizes are much smaller. So an owner in that sector takes on a huge financial risk on themselves. So we're trying to de-risk this financially. We're trying to come up with something that could be a demonstration of the technology, something that actually fits their vessels, something where they're not looking to deep sea vessels, or something that practically doesn't fit, and something that fits the operational environment. So if we were trying to solve this problem, I think a lot of people nowadays can agree that the first thing one might do is go on AI nowadays and ask AI, how would you solve this problem? What would you do for owners? So Wenjan. So I did that, and unfortunately, I think we can see some value in this project because AI has generated what appears to be a pirate ship with a jet turbine mounted to the deck and no remaining cargo space. So not very helpful, but also gives me a small appreciation that there is some value in this project, seeing as this isn't something that's been done before, something that's come from anywhere else. Next slide, please.
Rob, just considering Eugene will need to leave in 15 minutes, can we skip maybe the next few slides quickly?
Yeah, I'll go through these a little bit faster. So just to characterize the vessels, you can see an example here. So general cargo vessels, typically between 1,000 and 10,000 deadweight, between 60 meters and 110 meters LOI, working in regional and coastal waters around North European and short sea, so coastal areas around the UK, Ireland, and the Baltic and the North Sea. Traditionally, these are powered by medium-speed diesel engines, with some of the challenges there that I've already discussed about regulations, emissions, and the investment costs. So on the next slide, you'll see some information about the HEROZEC project, which has got 5 key tenants, which can largely be broken down into 2. So what Eugene will be talking about, Eugene from EcoMar Propulsion will be talking about in just a second, is the powertrain element of the project. So the powertrain supply chain for the fuel and the fuel storage. So Eugene will introduce himself and give you that information, followed on by Ahmet from the University of Strathclyde. We'll be talking about the novel gate rudder system and how that fits within the hull efficiency improvements to create a combined package of a potential retrofit package for vessels that an owner could adopt if they wanted to. So Eugene, are you happy to take over the next slide now, please?
Thanks, Rob. I hope everybody can hear me. I'm actually in a car park at the Ocean Terminal because I'm on a panel in 10 minutes. So unfortunately, I have to be a bit quicker than I would have liked to be. But if anybody has any questions specifically for me, please feel free to email me on the email that you see on the screen there. So I will speed through these. I know everybody's busy and we've all got stuff to do. So obviously, we'll start with the vessel itself. And the principle that we were looking at was how are we going to use 2 different kinds of potential fuel at the beginning of the project. And then we wanted to whittle that down so that we had one functional fuel that would meet the duty cycles, do everything that the owners wanted, in which case it's intradership, and also minimize the cargo losses. So can we go to the next slide, please? So while it starts changing, John, there we go. This is a little bit about who we are. I won't labour this a lot. You're more than welcome to look on the EcoMar website and find that out. So I think we'll skip this one and move on to the next, just to say that we've got a very good team from professorial level down to apprentices. Next slide, please. As you can probably tell from this, I've done a lot of preparation that I'm not going to be able to use, but we've also done an awful lot of practical delivery of machinery, including battery, hydrogen, and methanol technologies. So next slide, please. So we're not just about designing on paper, we're actually about making these things happen. Next slide, please, Wenjan. Again, the statement of value for the entire industry is huge, and it's increasing. I'm sure most of you saw yesterday's projection with the changes to zero emission and lower emission propulsion. So that really feeds into this whole HEROZEC project. So next slide, please. Yeah, so we looked at the whole project, and we were looking at, first of all, we took hydrogen as a potential, and we took methanol, and pretty soon discounted hydrogen. The energy density isn't appropriate for this kind of vessel, and therefore we ended up with methanol. We didn't investigate ammonia at this stage because the technology is by no means as advanced as it is for the other technologies, and the further you go along that hydrogen combination, it gets more and more complicated and more expensive. So we whittled it down to saying this is going to be a methanol powered ship. We have the existing motors in there, and then we looked at the conditions of whether it was viable to put an entirely new powertrain in, or whether we should retrofit and modify the existing powertrain. And it came to a conclusion that we had to modify the existing powertrain because the costs of retrofitting such a huge machine was prohibitive. The second part of it was to then look at the blend, how much methanol against fuel oil that we're going to put in there, and its efficiencies and all these sorts of things, and how it would fit in again with the regulatory environment and also the structure of the ship. And I think the physical structure of the ship is one of the key leading aspects to what we were looking at a later stage. And we ended up with a blend which we felt comfortable with. We corresponded that with the duty cycle of the vessel, and we were comfortable that the fact that it would provide the range, it would have sufficient surplus so that you could have contingencies in there, and also that it wasn't onerously damaging to the cargo capability. But next slide, please. So this is just an example of the decision-making process. It's very complicated. I'm sure that the slides will be available later, but when you start this process, you need to be really, really clear about where you're going and why you're going there. And so we ended up using this matrix to come to a conclusion, which I've already alluded to, which was that liquid storage with methanol was certainly the right solution for us. So next slide, please. We then also looked at, and I should stress, the engine itself. Can you change the engine itself? Can that be modified? In this case, it was the Caterpillar engine, so it was possible. And then we need to look at balance of plant and existing equipment, and then the ship itself. And this is the interesting bit for the naval architects, is how do you get that fuel on board that vessel, given the fact that it takes up more space than your existing fuels. And so we spent a lot of time investigating not only the regulations that we were looking at, which is IGF code and Lloyd's, but also about how we would change the ship over without it impacting stability, buoyancy, cargo, crew effectiveness, and all these multiple different aspects. And so the game that we played was a very complicated game of Tetris, in effect. And we played with a lot of different aspects, the sloshing aspects of the different fuels, and also cofferdams, where we would place those, whether we should put things on the deck, under the deck, and all these different variables. And we worked our way through it. So if we could go to the next slide, please. So these are the key considerations. We now had a state where we know how much fuel we needed. We knew the volume that needed to be put on board the vessel. We also determined what the fuel preparation areas were going to be. And with a gap analysis against Lloyd's Register, we were aware of where the pipelines needed to be, the vents, and so on and so forth. So the safety aspects came into it at a very early stage, and the consideration of cargo safety, efficiency of the vessel was all combined to provide our boundary conditions to work with. And then we were looking at whether it should be an actually placed new fuel tank, or whether it should be transverse, what effect that would have on the cargo, what effect that would have on the stability, and so on. So if we go to the next slide, please. And we experimented, as you'll see from these slides that we've flicked through now. There were quite a considerable number of aspects to look at, not only in terms of materials, but in terms of how we were actually physically going to place that in the vessel. And we came to a conclusion that we could manage the vessel by changing the hatches, welding down one hatch, and placing a nitrogen inertion tank on the top of that hatch, which met all the requirements and only removed 8% of the cargo. So we lost 8% of the cargo as the ship is currently, which was within the boundaries that we've been set. Next slide, please. So the effect of that is that the cost was minimised and the long-term value was maximised. So these, again, I will just skip through these a little bit, but these are further safety considerations. So you have to look at IGF codes, you have to look at bunkering, you have to look at how the excess gas or waste is vented and where the pipe runs are going to go. And this is all based on the existing ship, de-aeration, so on and so forth. And so what we did was we determined where these optimal choices were, and then took that as the next stage to make our other core decisions, which is an iterative design process that we worked all the way through. And at every stage, we referred back to the Lloyd's Register RGF code, and we also referred back to the principal who really wanted to know, which in this case was Rob, what is it going to do for my ship? Next stage, please. So the strategies that we came up with, as I say, we moved the deck hatch, we sealed 50% of the rear deck. We mounted a nitrogen tank on, which then creates an inert gas, which will enable us to meet all the safety requirements for the tanks as they deplete. It also allows us to purge those tanks as we go. And we looked at the orientation of the tanks and their positioning. And what we found was on the vessel, in this case, it had a false bulkhead that we could use. So we moved a lot of these smaller issues around. And we actually found that the vent location for the mast, there is a possibility to use the existing trunking and run it right along the ship and get it right away. So location 2 ended up being the preferred option. And given the fact that it wasn't under high pressure, that it wasn't any particularly onerous engineering, we considered that to be a much safer option than going anywhere near the wheelhouse. So next slide, please. And this is our final design. So having gone through multiple iterations, what we found is that by utilising the rules and positioning the fuel preparation room and the cofferdams and creating new transverse tanks, which you can see are in an L configuration, we were able to provide the fuel that was required, the storage capacity. We're able to inert that tank, we're able to meet all the IGF codes, and we're also able to maintain the stability of the ship without any adverse impacts. There will be a new balance calculation to be done, but actually the stability of the ship's not impacted whatsoever. So by the time we get to the final configuration, which you see in front of you, it's very, very simply put together, and it has no direct impact on the existing engine room or steering room. Next slide, please. It took us a long time to work these things out, but at the transition from the existing fuels, the financial side of things, the cost centres that we considered as in effect a contract for an intrada ship, we were looking at all these different engine modification, fuel handling systems, safety systems. These things have to be brought into the design process, and the earlier you bring them in, the better. I think one of the major issues that we discovered was that the Caterpillar engine is proprietary technology. So that one main issue that we found was very, very difficult to overcome. Now, if you go to those OEMs and get that other shipowners in the future, but as part of a development project in place, the supply chain is there. They're working on the fuel supply, and the fuel supply is limited at the moment, but in the short.
Sorry, don't know whether it's just me or everyone. So Eugene, we cannot.
I think we may be having an issue. Okay, sorry.
It's okay. Yeah, some words we heard. I hope that people will be able to gather the information from some keywords.
I don't know if you can hear me at all now, guys.
Yeah, now it's okay.
Are you back on? Sorry, apologies for that, everybody. My voice is going and now my internet's going as well. If we can go to the next slide, I'll sum up very, very quickly. I think just to reiterate what I was saying before, the fuel supply is available. It is growing. Methanol is becoming more available. Short to medium term, this is a viable option. So on the next slide, you'll show the costing and the cost of this. There we go. So even given the restrictions from Caterpillar, what we've found is that the energy supply and the motor transition is around about 2 to 2.5 million euros. There is finance available now for those of you who are interested in doing this stuff, which reduces the capex massively and transfers it to opex. It is a very viable, possible solution. And so the risk that Rob was talking about is reducing. I wouldn't say it's minimized, but it's definitely reducing. And for us, what we found was the project has been really valuable in not only collating all the regulatory environment, but also the economic and the financial stability for our clients, in this case, in Tradership. At that point, I will hand over to Rob and I'll leave you. I thank you and I apologise in advance for the early termination, but these things happen.
Yeah, thank you very much, Eugene. Appreciate that. What we'll do, we'll move on to the next slide where Ahmet's going to talk about the gate rudder system and that side of the project. I understand obviously from the slides that there's a bit of information there, and what I'll do at the end is we'll talk in the summary a little bit about financials and how those numbers are grounded. So the 2.3 million euros or the breakdown of those costs, how that fits within the financial risk. So how that compares to a new build essentially. So Ahmet, if you're happy to introduce yourself and please take it away.
Hello, everybody. Can you see my screen right now?
Yes, we can see that fine.
Good. Yeah. Good morning, everybody. I'm Ahmet Gurkan. I'm a computational fluid dynamics specialist and researcher at the University of Strathclyde. Today, I will be presenting the design a gate rudder for a 90-meter container vessel and its impact on powering performance that we explored within the HEROZEC project as the University of Strathclyde. Okay. I will begin my presentation with a brief background on gate rudder technology, including its history and the fundamental principle behind how it enhanced the propulsion performance. And continue, I will introduce our target ship, Scott Explorer. For the gate rudder design, we applied established optimization method that utilized computational fluid dynamics. I will share an overview of the fundamentals along with the validation and verification study. Then I will explain our optimization methodology followed by key results from the design validation, calculation, and model scale test predictions. The earliest version of gate rudder system was invented by Mr. Sadamato Kobayashi, and it was originally called the frame rudder. The concept was later tested and refined through research and development project at the National Maritime Research Institute of Japan, led by Dr. Noriyuki Sasaki. His key innovation was repositioning two rudder blades on either side of the propeller, controlled by a single rudder stalk, a design that led to the first associated patent, by the way. Further research and development efforts, which contributed from Newcastle University and University of Strathclyde, evolved the system into its modern form, featuring two separate rudder stocks. In 2027, the gate rudder system was first applied on a Japanese container vessel, Shigenabu, and it provided up to 33% saving compared to her sister vessel Sakura, based on the voyage data. Between 2021 and 2024, the Horizon 2020 Gators project, led by University of Strathclyde in collaboration with 18 companies across 7 countries, aimed to demonstrate that benefit of the gate rudder system as a retrofit on the 5,000 deadweight ton coastal cargo vessel MV Erge. Sea trials and voyage data confirms that the gate rudder system achieved more than 20% reduction in shaft power, highlight its efficiency and potential in real-world application. In this slide, I will explain the fundamental principle behind how the gate rudder system improves propulsion efficiency. For conventional rudder system, a moving ship and its rudder experience resistance due to their motion through the water. When the propeller operates at stern, it interacts with both hull and rudder, causing additional resistance due to accelerated flow of the water. This phenomenon, known as thrust reduction, typically accounts for 15 to 25% of hull resistance, and in some cases even more. For the gate rudder system, unlike conventional rudder, the gate rudder is positioned on either side of the propeller, rather than directly behind it. This relocation reduces total resistance caused by rudder. Additionally, the gate rudder generates a positive thrust force, meaning contributes to total thrust force, including the propeller. Furthermore, rudder blades create high pressure zone, which interact with the hull, producing an additional force. We call it pressure recovery force. As a result, propeller requires less thrust, leading to less water acceleration and reducing in the level of propeller hull interaction. This combination of reduced resistance, added thrust, and improving the pressure recovery is what makes gate rudder system significantly more efficient than the conventional rudder system. Our target vessel is Scott Explorer, is a 90-meter long container ship capable of reaching speed up to 13 knots. In this design study, our primary focus was on design condition, where the vessel operates 12 knots with a mean draft of 5.68 meter. However, we also considered trial load condition as part of the project as well. The Scott Explorer is equipped with ducted propeller system featuring 2.3 meter diameter propeller. For the gate rudder design and power prediction, we utilized computational fluid dynamics. In this slide, here's a key aspect of our numerical model. We used SAR-CCM, viscous-based CFD solver. Resistance and propulsion calculation were conducted using unsteady Reynolds model for both model scale and full scale simulations. Open water calculations and optimization were performed using steady-state Reynolds model. The volume of fluid model was applied to account for free surface interaction. Pressure and velocity coupling were solved using segregated approach. Depending on the simulation scale, we used K epsilon realizable and SST K omega turbulence models. All numerical discretizations were implemented using high order streams for accuracy. Ship motions was considered in 2 degrees of freedom. These are heave and pitch motions. Finally, propulsion calculations were performed using a modified virtual disk approach due to project workload and time constraints. This setup allows us to achieve reliable and efficient CFD prediction for the project. As an essential part of numerical approach, we conduct verification and validation study for different aspects of the project to ensure its accuracy and reliability of the simulations. The computational domain were designed following the ITTC's recommendation, ensuring compliance with the best practice for CFD simulations. As an aside, this slide also shows mesh generation process, which is essential for accurate solving the computational model. Mesh generation, or let's say, in other words, geometrical discretization, involves dividing the computational domain into small cells to create a solution matrix. For this study, we used Star CCM's trimmer mesh method. To ensure accurate flow resolution, we applied local refinement in high gradient flow regions, like around the hull, appendages, and the propeller, especially for the open water calculations. In this slide, I will give some detail on verification result of our numerical simulations. To ensure reliability of the CFD predictions, we conducted verification study using 3 different mesh structure with varying mesh density for each associated calculations. The grid independency was evaluated using Richardson extrapolation method as recommended by the ITTC. In addition to fundamental hydrodynamic outputs, we also verified the flow and pressure profiles near the hull surface were mesh independent, make sure these are mesh independent. The verification study were performed both model and full scale calculations, as well as the open water simulations. Sorry. These validation results, the calculated grid convergence index values confirmed that selected mesh structures provide grid independent results, ensuring the accuracy of the numerical approach. These verification steps were crucial in validate numerical consistency and reliability for our CFD simulations. In addition to the verification study, we conducted validation investigation were carried out for several key aspects. For the propeller open water calculations, the results show a deviation within 5% range when compared both measured and extrapolated data, confirming the accuracy of the calculations. For the model scale resistance prediction, the discrepancy between the prediction and observed values are constantly within 5% range across the range of model speed tested. For the full scale prediction, power predictions were in excellent agreement with the power measured during the sea trial, showing the deviation of just 1.6%. This validation result demonstrate that the accuracy of our numerical model is within the acceptable region, validating the reliability for particular applications. The optimization study were conducted following the established method developed in the Gators project. For more in-depth scientific detail, please refer the published paper displayed on the screen below. In this optimization process, the CAD preparation and optimization were managed using case software, while CFD calculations were performed using Star CCM, as I mentioned before. A key contribution in this work is the integration of MATLAB software for propeller selection for each newly created designs. The methodology used will be illustrated in the flowchart, and I will describe in detail with its associated stage. The preparation, at the first stage, the initial model and gate rudder design were imported into the optimization model. In the second stage, a fully parametric gate rudder design modified and fitted to the meet specification of the target ship. That is the CAD part, and I'm going to describe the optimization part. Gate rudder design was created based on selected design variables, ensuring the compliance with the geometrical constraints. At the fourth stage, CFD calculations were executed for the new design, and propulsion variable along with the rudder forces were exported. For the fifth stage, the propeller propeller selection adapted to the based on CFD results. For the 6-stage, additional calculations were performed with newly selected propeller and propulsion result along the rudder forces, and these are extrapolated. That is the full circle of one design creation. That is the methodology that we followed within the cases software. Based on previous experiences, three of the most sensitive design variables were incorporated into the optimization study under the HEROZEC projects. These are blade rudder angle, rudder tip bending, as you can see in the middle image here. The rudder profile camber. These three design variables were the focused design variables into the optimizations. Two parametric gate rudder model were developed, each based on different rudder configurations. Version 1, this configuration used the existing hull form with duct removing. There is no manipulation at the stern or shaft region of the ship. Version 2, this version involved a modification to the stern form to accommodate the positioning of the rudder blades as shown in the image. Each configuration underwent a separate optimization process. A detailed design of experiment study was initially conducted for the first version of the gate rudder system. For the second version, which involved significant change of the hull stern form, a gradient-based optimization approach was employed, utilizing insight from the first DOE study. In the first study, total 27 design points were created. In contrast, the second optimization study in version 2 included 46 design points. The correlation matrices were design points is provided on the image, as you can see. From the parametric investigation, we focused on propeller thrust and delivered power reduction as the key output parameters. During the parametric study, we were able to monitor the correlation between the selected design variable and output parameters. The DOE study revealed that the most sensitive design variable, as expected, was the rudder angle among the considered other variables. Considering the overall results and various flow characteristics, the best performing design candidates were selected from each parametric investigation. The first version showed significantly higher overall performance compared to the second version. As a result, it was decided to proceed with more detailed steps, including full-scale calculation and model test using the selected design from the first version. This design was also considered the more practical choice, as it requires only minor modification to the vessel stern. The stern form design was slightly updated to accommodate the gate rudder blades and its required motion. For the test campaign, a modular stern form prepared, allowing for accommodation of both conventional and gate rudder system. You are seeing the different rudder system and their orientation with the model test. To associate propeller for both systems were also manufactured, as you can see on the image. The model tests were conducted at the Kelvin Hydrodynamic Lab laboratory. The bare hull and appended hull for both rudder systems were tested under trial and design load condition, covering model speed equivalent to 8 to 12 knots. The propulsion tests were specifically conducted for appended hulls, of course, with the model speed range from 10 to 12 knots ship speed. Similar to the physical test, model scale CFD calculation were performed to validate the results. The effective power prediction from both EFD and CFD method match within a maximum difference of 2%. However, while the CFD calculations, gate rudder propulsion performance aligned closely with the EFD predictions, especially under trial load condition, there are significant difference between the EFT and CFD prediction for the conventional rudder systems delivered power. That is one important point that I should highlight here. A clear picture emerges when comparing the impact of the gate rudder and delivered power, especially when constrained with the conventional rudder system. This graph illustrates the power reduction prediction from different methods associated with various loading conditions. That is the EFT, sorry, that is CFD trial load condition, difference between gate rudder and conventional rudder. That is CFD EFT trial load condition, performance difference between GRS and CRS. That is CFD design load prediction differences, and that is EFT design load predictions. In all cases, the gate rudder demonstrate enhanced energy efficiency. The full-scale CFD calculations align with the model-scale CFD predictions at certain ship speed, as you can see. The purple represents the full-scale calculations, not extrapolations, and it matches with the CFD predictions at some point. Okay, I'm going to go to my last page. Under trial load condition, the EFT predictions show that the delivered power for the gate rudder configuration is between 4.6 to 12.9, lower than a single rudder behind a duct propeller. Computational fluid dynamics predicts estimates an even greater reduction. It's around 22%. Under design load condition, EFT predicts the PD between 2.6 to 9% lower for the gate rudder configuration, while CFD estimates reduction between 13 to 30%. The full-scale CFD calculations for design load conditions shows there is 17% reduction in average in delivered power with the GRS configuration. Based on experience, our experience, sea trials suggest that GRS configuration achieved additional 10 to 15% reduction in delivered power beyond predicted value. That is because of real environment. Therefore, even in the worst case scenario, the gate rudder configuration is expected to improve energy efficiencies by approximately 15 to 20% reduction compared to conventional rudder propulsion system. And I reach my conclusion of my presentation. Maybe I should stop here to leave stage to Rob.
Yeah, thank you very much, Ahmet. That was absolutely fantastic, Wenjuan. So I'm just going to summarise with a couple of slides here, and I know Wenjuan's already put in the chat box if anyone's got any questions. I've had a couple come through privately. If anyone's got any questions, please add them to the chat box now, just as I sum up. So just to summarise where the project's got us to and what we're going to do next. So the emissions reductions so far on the powertrain side have shown that we can actually reduce emissions by 55%. Which for a vessel like the target vessel that Ahmet told us about represents a reduction from nearly 500,000 kilos of CO2 per vessel per year down to around 211,000 kilograms. So you agree for leaving a largely conventional vessel with the changes that we've proposed here, you can save over 55%, which is a fantastic amount of CO2 reduction here. The target is to get to zero, but what we've had to do as a project is to consider how far we'd have to go with the retrofits, how many changes there would be. And it is possible, one of the variants we've looked at, which would involve a fuel cell, could get us to nearly 95% CO2 reductions. But we're trying to look at a pragmatic line of what's possible to get to the 2030 target and beyond that. So I think that's a really positive starting point, at least. There are obviously compromises that come with that. Eugene spoke about the fuel tanks, and you see how that was integrated. So one of the starting points of this project was looking at how the fuel could be modular. But unfortunately for the class rules, the legislation, what we have to do, we don't believe that modular is the solution. So that's one of the big takeaways from this, which actually shows that our original targets weren't entirely successful, but have taken us down a very positive learning path, is that we do need to integrate the fuel tanks in order for the stability of the vessel and the safety to be in place. We've got a cargo loss of around 8%. So just for context, 8% would be on a bulk stowing cargo, volume stowing. If it was deadweight stowing cargo, then that could be down to 0. So where you run out of deadweight in the vessel before you run out of volume. So 8% is only against the volume targets. So realistically, in terms of the operations that we see as a manager, that would probably be about 50% of cargoes reducing by 8%, and the other 50% would carry 100% of the cargo they were expecting to carry. In terms of the retrofitting costs, I said at the start, we'll talk about financials at the end. The worst case pessimistic cost for the propulsion system would be 2.3 million, and that would be euros, and that would be with significant changes beyond what the manufacturer could offer us. So actually that is a conservative estimate. We can possibly reduce those, and the remaining costs, the two blocks of 400,000 euros that Eugene showed, are for the physical modifications, so the fuel tanks and running the fuel lines to the engine, and for limited engine modifications. So actually that is quite a pessimistic prediction. The gate rudder system, we're talking about the region of €1 million to retrofit the gate rudder, and that's assuming it's done as a discrete job. So the fact that the two pieces of work wouldn't overlap, and obviously what you'd try and do with this package is to have concurrent works so that the dry docking costs are reduced. For context, I mentioned at the start that the average age of the fleet is around 27 years old. There's a couple of reasons for that. One is people holding on to assets that are currently functional. The other reason is actually there's a very limited amount of replacement value at the moment. The actual ability of the shipyards to replace vessels in this particular sector is not as high as it is in other sectors. So there's very limited production of this sector in China, the Far East, and India, and a lot of these vessels still come out of European shipyards. So the challenge with replacing vessels is that actually we wouldn't be able to keep up if people had to write off vessels when they couldn't meet the moving bar of the emissions regulations. So the €3.3 million most conservative estimate for this system would actually compare to around €12 million as a replacement value for a vessel with these technologies built in. So you can see we're around about 30% of that, which is actually quite favourable in terms of the reduction in total capex in order to achieve emissions compliance. So that's therefore actually the financial risk to owners is quite a difficult target to put a number on, but we believe that it's a significant improvement on having to replace an old vessel. And the numbers also are complemented there by the 15 to 20% reduction in fuel consumption under the gate rudder system. So that shows that not only are we trying to improve the powertrain, but there'll be reduced drag. So the total fuel consumption on this vessel would be less as well. So therefore you've got further savings. And the OPEX of the vessel is something that we're continuing to investigate here. So next slide, please. So as I just mentioned there, we believe there is a need for green retrofits. The idea that vessels are going to be replaced with an all singing, all dancing version of the latest technology, we don't see as feasible or realistic. And so we believe that we have come up with something that, albeit short of demonstration at this point, is a viable option for owners to look at as a retrofittable package where they are able to keep up with the new emissions regulations. We've looked at various technology options, and we've actually narrowed this down. So as Eugene spoke about, we started off with quite a broad scope to this, and methanol wasn't a predetermined fuel. It was something that we narrowed down by looking at an entire spectrum of different options that are currently available. In terms of the economic viability, we've put together a business case showing that there are potential for savings here, particularly when your baseline may be replacement. We are still working on the OPEX against a current vessel, but we know that necessarily the OPEX won't be more favourable than the status quo, but that doesn't include the moving part of emission regulations, and that's something that we'll be summarising at the end of this project. So we spoke at the start about the regulatory and market drivers. We know that there is a moving bar, and unfortunately that moving bar means that owners have to consider that OPEX against what will be happening in 27, 28, 29, 2030, not against what's happening today, because it's fine saying that we've got lower OPEX today until you hit the cliff edge of your vessel may not trade at all. It's not a moving bar of you can continue to have lower OPEX by sticking with the status quo. There'll become a point where that expires and something has to be done. Obviously, with challenges and barriers to this project, there are high upfront costs as opposed to status quo. There's a higher capex than status quo, and there's a number of uncertainties. So we've put a lot of modelling into this in terms of the variables in this situation. So not considering those variables to be constant at today's prices, such as the availability of fuel and the price of that fuel, we've had to consider that moving bar. This also, we've not considered any financing or incentives here. So we've only really looked at this as an owner spending money on their own account rather than any sort of incentivization from the government. And yeah, so I think the next stage for here, which we maybe there's a question about, is about running potentially a pilot project or a demonstration of this would be the next obvious step. I believe that's the last slide of what I'm going to say. So I think what we'll do is go to the questions. The first one I can see, I think I've just answered actually. Are we only addressing methanol fuel cells? We aren't only considering methanol fuel cells. Actually, the solution that Eugene spoke about is methanol blended in the main engine. So modifications to the existing main engine. The methanol fuel cell was considered. The methanol fuel cell could give us savings of around about 95% of emissions, but the capex starts taking that wildly away from feasible. So actually looking at methanol reformers was one of the key things we found. So given the size of the main driver on this target vessel, the reformers were going to cost in the region of €2 million. So that'd be an additional €2 million on cost just for the reformers before the fuel cell and all the other modifications. So what we've tried to do here is pick a pragmatic line down the middle of what is currently available and what would be the most economic proposal for an owner. So hopefully that answers that question. Which is the expected uncertainty on the estimations for the gate rudder? So Amit, I wonder if you could come back in and discuss that, please.
Okay. I don't know if it's a question or a statement. Maybe Professor Attar, you may.
Yeah, thank you. And I will handle that. I noticed that the question came from my colleague, Professor Theotakatos, and then who is also in the project partner, and then he could have asked me directly during the project. Okay, so moving away from the philosophical side, it's a good question, and then there are actually the differences, what we predict in the CFD, and as well as to the model scale and then the full scale. To give him the exact figure for the uncertainty, we need more data. At the moment, there are 8 existing, if you like, the vessel fitted with the gate rudder, and then our latest vessel through the Gates project was the 9th one. They all indicated 15% plus saving in the full scale. So therefore, we need more data to tell the uncertainty levels for Makis. But on the other hand, the reality is we had the difference at the moment between the full-scale predictions and then the model scale and then even the CFD predictions. And then currently we have been working on it. But the good thing is in the full scale, in the trials, we all have quite attractive predictions, quite attractive saving for the vessel. And then I believe currently the gate rudder system is the best energy saving devices that you can apply a general commercial vessels. That's all I can say at this stage.
Thank you very much for that, Mehmet. I think hopefully that answers the question. I think that was very clear. Thank you. Just looking at the questions in the chat box again. So Evo, I see your question about direct electric final drive. It is something that was considered. So the fuel cell would actually be paired with an electric final drive. What we see whilst we are building vessels in Holland is there seems to be now roughly a 50-50 split. We know it goes through waves of trends where electric final drive moves away back to direct final drive. The target vessel is a conventional arrangement, so that's direct final drive. We did consider the electric final drive, but again, the modifications for that to move away from one system to another would make it prohibitive. We actually do believe that that there would be potential benefits there, but it would be such a significant change to the overall arrangement of the vessel that we decided to stick with the conventional final drive, which actually a significant proportion of the older vessels do have. It's the ones that are currently being built and built in the last 2 or 3 years that seem to be moving away from that. And that was one of the big actual starting points of this project. We were considering about whether the electric final drive was the way forward, because obviously you can modulate, you can generate modular power. Excuse me. The modular power could come from generators or alternative forms of energy generation, and we did look at those, but it would be such a significant change to the target vessel that it didn't make economic sense for us to convert the vessel to electric final drive. Albeit I do believe that's something that will probably become more prevalent in the next couple of years. Ines, I see your question in the box as well. So have we considered or looked at how relatively low cost generator distribution system modifications or enhancement aids decarbonisation? We didn't look into this. It was a slightly bigger project than that in terms of I guess the wider, bigger picture scope, rather than looking into that detail. But I will make a note of that and take it away. That sounds like a really interesting comment. Thank you. And the question Orla's just put in the chat. For the sea trials, how is the percentage reduction calculated? So Ahmet, another one for you, please.
Yeah, okay. In fact, maybe we should answer this question by the examples that we dealt as a University of Strathclyde. There were 2 vessels that we involved. One of them is the Japanese container vessel. Japanese container vessel has its sister. I mean, one Shiganabo fitted with the gate rudder system, and the Sakura fitted with the conventional rudder system. From their trial report and voyage monitoring system, we are able to compare, make a comprehensive comparison between the 2 different systems powering performance. On the other hand, the target vessel of the HEROZEC, the target ship of the Gators project called HEROZEC, we performed during the Gators project period. We performed sea trials before retrofitting and after retrofitting. That is the 2 different ships and 2 different data where we are able to make comparison between 2 different systems in trial condition. I don't know if that addresses the question or last question. Otherwise, for the HEROZEC project, we directly make the calculation, perform calculation in full scale and model scale. But let's focus on the full scale part for both propulsion system, and we done direct comparison.
Lovely, thank you for that, Ahmet. I think that was certainly clear for me, so hopefully that answers the question. Just noticed the time; it's 11:59, so I think we're gonna have to wrap up there. But I'd just like to say thank you very much for MarRI-UK, Wendran and Orla for hosting this. Thank you very much for Ahmet and Eugene for presenting in great detail about the work that we've been doing. And thank you everyone else for attending. I hope it's been a very useful and interesting session for you. Wendran will share the contact details for myself, Ahmet, Eugene, and all partners in the project. And I think they'll be sharing